Here's an excursion, as your book calls it, a venture that's related to what we're doing. We just went through volumes in 3 dimensions. How about the volume of a unit sphere, a sphere of radius 1 in various dimensions? In 1 dimension, it's pretty easy, right? If you have a 1-dimensional sphere at 0, then you go 1 unit for a unit sphere on each side, and the volume enclosed, the length, is 1, 2 units. So we'll say the volume L is 2 in 1 dimension. Now in 2 dimensions, what we do is we think of taking this line and rotating it around like this and creating a circle. And now at each point along the original line segment, we have a height here of square root 1 minus x squared twice. It's down and up. So to find the area enclosed, the volume of the 2-dimensional sphere, we'll integrate twice this height, twice square root 1 minus x squared, going from back here to back here, right, the height of this thing all the way across. What does that come out to be? This is one of your integration techniques, right? If you see a square root r squared minus x squared in there, you can draw a little triangle like this. And if I make the hypotenuse 1, whatever this is the square of, minus x squared, and put 1 and x like this. Remember how to make the triangle square root 1 minus x squared on that side. I can use the substitution. X equals sine theta, dx equals cosine theta d theta. Whenever I see the square root 1 minus x squared, often that makes the integral easier. What happens here? Square root 1 minus x squared by the triangle is this over is cosine theta. Dx, we said, is cosine theta d theta. And the integral of twice the cosine squared, well, by the half angle identity, cosine squared is 1 plus cosine 2 theta over 2. So we have to integrate 1 plus 1 half cosine theta. 2 theta gives us x, and that should be a fourth. No, that's right. Yeah. Gives us theta plus 1 half sine 2 theta evaluated at minus pi and 0 gives us pi. Sure enough, pi r squared is the area of a circle. Pi is the area of a circle of radius 1. What about the sphere? Now we think of this and rotating around into the 3rd dimension. Here's a cross-section. Each cross-section, when this little line segment revolves around in a circle, becomes a disk. So this time we have to integrate by the method of disks from minus 1 to 1. The area of the typical disk, pi radius squared, but the radius is square root 1 minus x squared. If your x units out, it's square root 1 minus x squared up. So pi radius squared is pi times that square root squared. That's an easy integration. You get 4 pi over 3. And it makes you wonder, what would be the volume for n dimensions if you keep going like this, doing the same thing? You find out you can actually deduce a formula. Here's from Wikipedia. The volume of an n-sphere, when you start seeing the pattern, is for in even dimensions, pi to the n over 2 over n over 2 factorial. And in odd dimensions, this is the floor function. It's the greatest integer less than or equal to n over 2. Pi to the floor of n over 2 times 2 to the ceiling of n over 2. That's the biggest integer, the smallest integer bigger than or equal to n over 2. All over n double factorial means n times n minus 2 times n minus 4 and on down until you get down to 1 here. So there's this nice formula for it, and amazingly, if you work this out, you can ask yourself, in what dimensions does the sphere of maximum volume occur? Here's what we get from the formulas. And in 1 dimension, the volume was 2. In 2 dimensions, the volume was pi. In 3 dimensions, 4/3 pi. In 5 dimensions, it's 1/2 times pi squared is about 4.9, etc. And what you find out is that actually, in 5 dimensions, the unit sphere has the greatest volume, and then it starts coming down again. So there is a dimension, it's 5 dimensions in which the unit sphere has the greatest volume. We've just been doing surface area. You do the same with the surface area. You find out the surface area of a sphere, unit sphere, is maximized in 7 dimensions. Kind of an interesting excursion. I thought it was maybe worth waking us up today. The main topic, however, is line integrals. This is so you don't get too bored with the rest of the lecture. I put that up there. How about scalar line integrals? There's actually two types of line integrals we're going to introduce, a scalar line integral and a vector line integral. And the vector line integral is defined in terms of the scalar line integral. So what is a scalar line integral? It has this interpretation. If you have a curve in the xy plane, you can think about a surface z equals f of xy over that curve, in fact over the xy plane, and then over that curve there's an image of that curve within the surface. Suppose I wanted to find the area of this curtain below the surface and over the curve in the xy plane. That's what geometrically the line integral is going to compute for us. What we'll do is along this path we'll increment this little curve here into little tiny arc lengths here from point A to point B, and along each arc length we'll take a curled rectangle. In other words, we'll take this curve here and extrude it upwards to the surface, not to the surface but to a height of the surface somewhere in an intermediate point. So we'll take a rectangle over this spot, and over here we'll take this rectangle over this spot that has a height somewhere along the image of the curve within the surface above the curve. And so if we add up the areas of those rectangles, that estimates the area of the curtain. And if we take the limit as the number of little subrectangles goes to infinity with the width of the widest one going to 0, this is what we get. Limit as n goes to infinity, number of subsegments. Here we've incremented the curve into all these little subsegments. That is, you partition you've got a parametric curve, right? This curve written as a function of t. So you take the t interval, a to b, break it up into n subintervals. That breaks your curve into n little arc length subintervals. For each of those, you put a rectangle above it. And add up all those rectangles, take the limit. So this is the limit as n goes to infinity, number of segments here goes to infinity, of the height of the function at some intermediate point, times delta sk, the arc length below. So it's a curved rectangle. And we'll define that to be the line integral. One interesting immediate result is that if you put f equals 1 in here, then this becomes limit of the sum of delta sk, which is the integral of r prime of t dt from before. I'm sorry. Let's see. Yeah, this is the arc length of the kth integral, and if you go from a to b, this actually gives you the arc length of the curve. So the scalar line integral from a to b gives you the arc length along the way by this calculation, because it's just limit of the sum of delta sk, which is how we defined arc length before. So now this may not exist in the limit, but when it does, we have some theorems that apply, right? For one thing, in order to be able to calculate this thing, you could say, well, if f is continuous and in addition you have this, oops, wrong way. If r of t, the position vector sweeping out the curve, is defined on an interval t going from a to b, and suppose that f and r prime are both continuous, then you can say that the scalar line integral, the area of the curtain if you like, is the integral from a to b of f of xy times r prime of t dt. That's a theorem. You can prove that that limit of that sum actually comes out to this amount. And then, of course, if you stick in 1, you get precisely what our definition of the arc length. Okay, now we call ds the arc length differential sometimes for that reason. And now this generalizes to 3 dimensions. In 3 dimensions, similarly, you can follow a curve in 3 space, and the line integral f of x, y, z ds has this theorem that you can evaluate it by, provided f and r prime are both continuous again. Integral of f, x and y and z written as functions of t by their parametric representation, times length of dr dt, dt, that says over there. So let's do an example actually. Suppose we want to compute the line integral of the square root of 1 plus 9xy ds. What's the area under this function, the square root of 1 plus 9xy, along the curve y equals x cubed, x going from 0 to 1, right? Well, to compute the line integral, we first have to write this in parametric form. So let's let x equal t and y equal t cubed. No sense making it hard, right? Let's do the easiest parameterization we can think of. Then t will go from 0 to 1 since x equals t. So x equals t, y equals t cubed, let t go from 0 to 1. Then we find the length of r prime of t, because we need it in the formula. R prime of t is the square root of dx dt squared plus dy dt squared. Well, if dx dt is 1 and dy dt is 3t squared, we square root sum square of those and we get 1 plus 9t squared for r prime of t. And now the line integral with this r prime and this parametric curve, representation of the curve, is of square root 1 plus 9xy is integral t goes from a to b 1 square root 1 plus 9 x of ty, you have to replace x and y with their functions of t, times length of r prime of t dt. And r prime of t, recall, was square root 1 plus 9t to the 4th, actually. 3t squared squared is 9t to the 4th. And then times 1 plus 9x is t, y is t cubed. This one is also square root 1 plus 9t to the 4th. The square roots together make 1 plus 9t to the 4th. It's a cooked problem, right? We have to integrate 1 plus 9t to the 4th from 0 to 1. That's easy, right? It's just integrating a polynomial and we get 14 fifths that comes out to be. For the area of the curtain, if you like, below the curve, square root 1 plus 9xy, over the curve, under the surface, over the curve y equals x cubed. So there's an example of actually computing it. You use this theorem. You write a parametric representation of the curve, you find r prime of t's length, and you put in the values of the parametric representations of x and y and r prime of t, and just do a normal integral from calculus 1. Alright, well, a curve with r prime continuous, as in the last example, is said to be smooth, so we call it a smooth curve. It doesn't have any of these corners in it like this. What if we have corners in it? Well, you can do a little better. You can apply this theorem actually along curves that are only piecewise smooth. The theorem applied to smooth curves, we're going to say actually we can break it up into if we can break a curve up into the union of curves, a finite number of curves, each of which is smooth, then we can evaluate the line integral. If you look at the definition and think about it a while, that limit of the sum is equal to the sum of these limits of sums along C1 plus C2 plus Cn. You can just add a bunch of line integrals along the individual smooth curves together to get the line integral along the piecewise smooth curve. So there's a little generalization. Also, we said you could do this in higher dimensions. Let's try this harder one. The line integral in 3 dimensions of x times e to the z squared ds. All right? Well, we have to, if the curve goes from, in 3 dimensions, from 0, 0, 1 to 0, 2, 0 to 1, 1, 1, we have to write that parametrically. So if I want to go from 0, 0, 1 to 0, 2, 0, well, let's see, I could let y equal 2t, and then y would go from 0 to 2. That's an easy parametric representation for y. 1, y would go from 0 to 2, and then if I want t to go from 1 to 0, I could let z equal 1 minus t at the same time. This is a piecewise linear curve. The idea is that since y and z are both constant times t plus a constant, this will make a line segment. Remember that from parametric curves. If you have x equals at plus b, y equals at plus b, then you're sweeping out a line segment. This is sweeping out a line segment in yz space while x remains 0, and you go from this point to this point. So, and then we'll go along another line segment from 0, 2, 0 to 1, 1, 1 by letting x equal t. It'll go from 0, x will go from 0 to 1, so x is t, and t goes from 0 to 1, that says. And then y has to go from 2 down to 1, so we'll let y be 2 minus t, and then as t goes from 0 to 1, y will go down to 1, and then z will be equal to t, will go from 0 to 1, and since these are all linear functions, a number times t plus a number, this will sweep out the line segment from this point to this point. Now we have a piecewise linear curve. Kind of sketchy this, put it somewhere, oh well. But it goes along the line segment 3 space from 0, 0, 1 to 0, 2, 0, and then it takes a sharp corner and goes to 1, 1, 1. We can evaluate the line integral along this curve by breaking up into two pieces along C1 and C2 and adding them together. So we'll integrate x e to the z squared, replacing x by x of t and z by z of t. They're parametric representations. ds gets replaced with length of r prime of t dt. Similarly over here, ds gets replaced with r prime of t dt, x of t and e to the z of t squared, but we broke it up into two pieces. On this piece, see, x is equal to 0, so we integrate 0 times something, we just get 0. But on the other piece, x is equal to t, so we replace x with t. Z is equal to t, so we get e to the z squared, z to the t squared. And then r prime of t. What's r prime? Well, dx dt is 1, dy dt is minus 1, dz dt is 1. So we root sum square the component, those three components to get length of r prime is 1 squared plus minus 1 squared plus 1 squared is square root 3. We have to integrate square root 3 times t e to the t squared from 0 to 1. And that's not so bad. A substitution, u equals t squared makes du equal 2t dt, and 1/2 du replaces the t dt you see. So this becomes 1/2 the integral e to the u du. Still happens to go from 0 to 1. Right, since when t is 0, u is 0, when t is 1, u is 1. And now this one isn't hard to integrate. This is just square root 3 over 2, e to the u evaluated at 1 and 0 take the difference. It's square root 3 over 2 times e minus 1. There's a harder line integral in 3 dimensions with a piecewise smooth curve. That's as hard as they get for the scalar line integrals. This is kind of a hard section, isn't it? So we move on, and we'll just mention a few theorems apply. When two line integrals exist, you have your same results from calculus 1 you probably would have guessed. We'll just write them real quick. We don't want to go through all these hand-waving proofs to say. If you look at the definition, it's obvious that, and from the definition, it is obvious that integral f plus g is equal to integral of f plus integral g. Works for line integrals as well as for what you did along the x-axis. A constant integral can come out. And then I thought I'd mention an application. What good is this besides finding area of your curtain that's a variable height, right? Well, it applies to density functions. If you have a density along a straight path, we already learned before, you just integrate the density function. Now if it's along a curved path, you just integrate the density along the curve. And this might be a mass density, you get mass. It might be a weight density, you get weight. It might be charge density, and you get the total charge along the way. You can integrate some sort of a heat to get the total heat effect and so forth. People use this in lots of applications. So that's the utility, is generally with density functions. All right, besides doing the curtain area. Vector line integrals is the second topic. It's also in this section. It's a very long section. The vector line integral, however, is not to be scared of. When you write this, integral f dot dr, this is notation to mean f dot tds, where t is the unit tangent vector. Remember, r prime over r was the unit tangent? It only works if r prime isn't 0 along the curve. And then what happens is, if f is continuous, this vector valued function, and r prime is continuous and of one sign, then this can be evaluated, and we call it the vector line integral. What good is that? It turns out that this is how they define work. This is very important in engineering, physics, and so forth, lots of other places too, lots of sciences. The following theorem is usually used to evaluate this line integral. It has this vector line integral. It has this definition in terms of the scalar line integral. Right? You integrate f dot t scalar line integral, where t is the unit tangent vector, is the vector line integral of f. Along a regular parameterization, r prime of t never being 0 and being continuous, the line integral can be evaluated simply as integral of f dot r prime dt, even easier than the scalar line integral. Actually, the scalar line integral often isn't easy to do, so it's good it's easier. We can do the proof very easily. I'll mention this one. I think it's kind of nice and insightful on this one. Integral f dot dr is defined to be integral f dot t ds, the scalar line integral, but the scalar line integral of f dot t is f dot t times r prime of t dt. Went off the end of the paper here. So it's integral integral of the integrand f dot t, r prime dt is the ds by the theorem for scalar line integrals. But now t is r prime over r, and the length of r prime here cancels the length of r prime here, and you get f dot r prime dt. That's the theorem. So it's a very easy theorem, and it gives you a little feeling for why this works. However, there is one interesting thing that's happened along the way. Unlike the scalar line integral, where it doesn't matter which direction you move along the curve from point A to point B or from point B to point A, you always get the area under of the curtain. It's the same sign. If you integrate this one in opposite directions, if you integrate along the curve C going this way, you actually get minus the value that if you integrate along the same path going the opposite direction. We call that curve minus C. So the integral along the curve minus C f dot dr is actually minus the integral going in the other direction along C f dot dr, the work or the line integral. Here's an example of evaluating one. Since we have this wonderful theorem, we just apply it to integrate f dot dr, the vector line integral, with f equal the vector, let's say y minus x. Remember that rotational vector field? And suppose we move along the curve y equals x squared from 0, 0 to 2, 4. There it is. What should we do? First, write a parametric curve. All these problems require parametric curves. So we do it the easiest way we can, like x equal t and y equal t squared to move along this y equal x squared. Then t will go from 0 to 2. And we have to integrate f dot dr, where this is f was given. Well, we use the theorem. It's f dot dr dt dt, t going from A to B. Now what's dr dt? We just take the derivative of these, right? Derivative of x is 1. Derivative of y equals t squared is 2t. We replace y of t and minus x of t and f with their parametric representations. Y of t is t squared, minus x of t is minus t. And so we've got to integrate this, calculus 1 integral, right? This times this is t squared, this times this by the dot product is minus 2t squared, so we're integrating minus t squared from 0 to 2. Comes out to minus t cubed over 3 from 0 to 2 is minus 8/3. There's the value of this line integral. If you were doing work, you'd say the work done by this force is minus 8/3. Wait a minute, how can I do negative work? Well, remember, work isn't like our lay definition of it. If you hold a weight up over your head all day, pushing up, and it gradually comes down, you've done negative work, because gravity is doing the positive work against you. So this is just saying that as it moved, this force actually accomplished negative work. That can happen. Now, theorems for piecewise smooth regular curve C that we just mentioned the theorem applies to. You can apply these results. Integral, if the line integral of f dot dr and the vector line integral of g dot dr exists, then the line integral of f plus g, that plus didn't come out very well, is line integral of f plus line integral of g. Right? If you have a constant in a vector line integral, it comes out. And you can break vector line integrals if you go on a path that's C1 union C2, then you can take, just like in the scalar line integral, because of that, you deduce this theorem immediately, right? It worked for the scalar line integral, and the vector line integral is defined as a scalar line integral, so if you have a union of two curves, the line integral is the line integral along the first one plus line integral along the second one. At the end of these, you just add all n line integrals together. Alright, it's analogous to that theorem in calculus 1. If you integrate from a to b, it's the same as the integral from a to c plus the integral from c to b. Same concept, right? So I said one application is work. Why would we define this to be work? Well, the idea is this. Remember before you had said the work along a straight path was integral f dot a unit vector in the direction that you're going, dx. In other words, you integrated the component in the direction you're going. So you had to take the projection of the force out onto the unit vector in the direction you're moving. You took f dot u. Well, we're doing the same thing here. If we move along a curved path, we'll just say that you want to integrate the component of force in the direction you're moving at any time. So you take f dot the unit's tangent is this little vector here, and you just integrate that, the length of that thing along the curve. You're integrating the component of work that's pushing you along the path, and the component of force that's pushing along the path to get the work. So that's what I wrote here. Integrates the component of force tangent to c, which can be negative if this component is pushing against the direction you're moving. Alright, calculate the work for this special case. Suppose f is this function in 3 dimensions. X, y, y, z, x, z is your force field, right? And you're moving along this curve given parametric length 3 dimensions by t squared, t cubed for t between 0 and 1. What a mess, huh? Integral, the line integral, the work, f dot dr is, by our theorem, f dot dr dt dt, simple, right? Easy theorem. We put in f, which is xy, with, well, if x is t and y is t squared, it's t times t squared. Then yz is t squared times t cubed. Xz is t times t cubed. So we put in what x, y, and z are in f. And then when dr dt is the derivative of this one, right? 1, 2t, 3t squared. We dot product those, right? And we get this simple integral from calculus 1 that comes out to be 27/28 of all things. There it is. These actually aren't so bad. The vector line integrals are usually easier than the scalar ones because you get rid of that nasty square root. Other notations I just wanted to point out. I hope you can read this. It's really tiny, isn't it? Let's blow it up a little. Okay. Not good. Alright. You'll also see this, integral f dx plus f1 dx plus f2 dy. What does that mean? Where f1 and f2 are actually functions of x and y. This means the same thing. F dot dr is also given this notation if f is f1i plus f2j, two functions of x and y. This means the same as that. Don't let it throw you. It's just like calculus 1 where you get umpteen different notations for the derivative and so forth. So here's an example. This is actually repeating our previous example. Suppose I move along x equals t, y equals t squared from t going from 0 to 2. Remember the parabola that we did? And we want to integrate y dx minus x dy. How do we do that? It's very easy. You just replace dx with dx dt dt and dy with dy dt dt like that. And you get, well, y is t squared along this curve. Dx dt, take the derivative of x is 1.